So in this video, we're going to talk about ideal gas law. So this law is first stated by Benoit Paul Emile Clapeyron in 1834. Just kidding, I don't know how to pronounce it. So let's just use Clapeyron.
I never found you funny. I never found you entertaining. I never found you smart. I just found you annoying.
So this is also called as the general gas law. This law is the equation used to describe the ideal gas. So when we say ideal gas, we have some assumptions. First one, the particles have no force acting among them. So it's like they are inert, or for students, they are stoic.
Now I'm getting angry.
These particles do not take up any space, meaning they don't have volume. In real life, they have. But here we're going to ignore their volume. So you will learn more about this in the kinetic molecular theory of gases. And we also have non-ideal gases and real gas, or the real gases. The real gases or the non-ideal gases represents how gas actually behaves in real life. Okay, so for now, we're just going to focus to ideal gases.
Excuse me?
Okay, so the formula for this is PV is equal to nRT, where P is your pressure, V is the volume, N is the number of moles of gas, T is temperature, and R is the universal gas constant. And R has many values.
What? That is shocking.
It depends on what unit you're going to use. So you can use joules per mole K, millimeter mercury, liters, etc. Okay, so in chemistry, this one is commonly used. So some books, they use 6 instead of 5. So that's what we're going to use. So PV and RT, we can have this equation. PV over nRT is equal to 1. This is also called as the compression factor. A gas can be called ideal if all of this are equal to 1. Okay, so this also means that P is directly proportional to N and T because they are on opposite sides. And P is indirectly or inversely proportional to V since they are on the same side. So meaning when P increases, V decreases. Okay, so let's try to solve this. A sample of gas at 25 degrees Celsius has a volume of 11.0 liters and exerts a pressure of 660 millimeter mercury. How many moles of gas are in the sample? Okay, so using this formula PVNRT, let's isolate N since that's what we're looking for. So temperature, let's convert this to Kelvin. This will give us 298.15 Kelvin. Pressure is 660 millimeter mercury. And as you all know, we're going to use atmosphere. But hey, you can also use millimeter mercury if you want. Just want to show you how to use atmosphere. Later, we will have millimeter mercury.
Ooh, just what I've been waiting for.
So converting this will give us 0.8684210.526 atmospheres. So please do not round off yet. Substitute all the values given. 0.868 times 11, that's the given here, over the constant R, this one, 0.08206. Kelvin here will cancel, and atmosphere will cancel, as well as liters. So this will give us mole, right? So if you remember your algebra, this will just be transferred in the numerator. This will give us 0.3904421.559. And considering the number of significant figures, we'll use 4 significant figures, which is 0.3904 moles. Very easy.
I was playing.
Okay, let's have this. Calculate the approximate temperature of a 0.300 mole sample of gas at 780 millimeter mercury and a volume of 6 liters, 6.0 liters. Okay, so again, the ideal gas law, PV Then since we're looking for temperature, isolate T. This will give us T is equal to PV over NR. Now remember, as I've said earlier, we're going to use millimeter mercury. Okay. we have this. If you're given pressure in different, what do you call this, unit, you can use it as is. You don't have to convert it to atmosphere. Unless the question is looking for atmosphere. Substitute all the values or insert all the values. This will give us this equation. Now solving for T, this will give us 250.1483251 Kelvin. The final answer in Kelvin will be 250 Kelvin. But since I want to use Celsius this time, just to show you, I'll use the formula temperature Kelvin is equal to degrees Celsius plus 273.15. Transfer this one here to get degrees Celsius. 250 minus 273.15. Our final answer will be negative 23.0 degrees Celsius.